Hello everyone, and welcome to my channel. My name is Nick Malloy, and today I'm going to provide you with a demonstration of the tutorial Sea Level Rise around Humboldt Bay. As our climate continues to change, the implications for coastal regions are profound, with sea level rise presenting one of the most pressing challenges. In this tutorial, we'll explore what sea level rise could mean for Humboldt Bay, a focal point of ecological, economic, and social significance in Northern California. But here's the thing, we're taking a simplified look at sea level rise. The real deal with storm surges, tsunamis, and all the tidal variation can be even more drastic. So while we're getting a glimpse, remember that the full picture is a bit more complicated. This demonstration is based on the written instructions provided in Canvas. Sometimes we update them, so you should always use the written instructions when following along with this video. Also, check Canvas for specific instructions on what you need to turn in at the end. Different instructors might have different requirements for this assignment. Okay, let's get started. Setting up your workspace. Begin by setting up your workspace. Start by creating your project folder on your computer's desktop. You can call the project folder Sea Level Rise. Be sure that there are no spaces in the name, as this can cause problems. You can use an underscore instead of a space. This course uses a standardized folder structure to help you keep your data organized. Inside the project folder, you should create 3 subfolders: Original, Working, and Final. The original folder is for storing unaltered copies of your data. The working folder is either for working copies of your data or data sets you create during the project. The final folder is for storing your outputs, such as tables, reports, and the final map layout. Setting up a project in ArcGIS Pro. Next, you should launch ArcGIS Pro. If it's your first time working in ArcGIS Pro, you might be prompted to sign in. On the ArcGIS Pro homepage, click Map under the New Project options. When the Create New Project window opens, name the project Sea Level Rise. It's fine to use spaces here. The next 2 steps are important, so don't skip them. Click the file folder icon so that the location is set to your Sea Level Rise folder on the desktop. Then uncheck the box next to Create a new folder for this project. The only time you would leave this box checked is if you started here and still needed to create a project folder. In this instance, you don't need to create a project folder since you already did that earlier. When you create a project in ArcGIS Pro, several elements are added automatically to your workspace files. Open the project folder in Windows File Explorer to see what's inside. You should notice that beyond the 3 subfolders you initially created, Original, Working, and Final, a few other items are added to your workspace, such as a geodatabase and an ArcGIS project file. Never delete any of these folders and files from your workspace, or you run the chance of corrupting your project. In ArcGIS Pro, you can see these default files in the Catalog pane by twirling open the folders. Spatial Analyst extension. The steps in this activity involve using the Spatial Analyst extension. Ensure this extension is activated by checking the licensing status under the application settings. It should say yes next to Spatial Analyst. If it does, then you're fine, and you can move on to the next step. If it doesn't, you'll need to configure your licensing options. Refer to the images in the instructions for more details. Downloading the project data. Now you need to download the project data. You can find direct links to these datasets in the written instructions. The link takes you to a Google Drive download page. Once you're there, click the Download button. It should automatically save to your Downloads folder. Copy the data from the Downloads folder to your original folder. Next, use 7-zip to decompress the file. Once it's done decompressing, go ahead and delete the original 7z file. In ArcGIS Pro, you may need to refresh the original folder to see the files. Checking the spatial reference system. For every analysis, it's important that each dataset you use shares the same spatial reference system. ArcGIS Pro makes it possible to view overlapping datasets with different spatial reference systems using Project on the fly. However, this feature can hide spatial errors such as datum shift. For a review of spatial errors and datum shifts, check out my video on how to understand spatial errors in map datums and projections. To prevent unwanted spatial errors, you need to check each of the datasets provided for this project. Then you will use the Project tool as needed to create new datasets with the desired spatial reference system. Since we are working with data located in Humboldt County, the spatial reference system we will use is NAD 1983 UTM Zone 10 North. In the Catalog pane, right-click the file named DEM-clipped and open the properties. Then check the spatial reference system. Okay, this one looks good because it's using the spatial reference system I want, NAD 1983 UTM Zone 10 North. Do the same thing for the two shapefiles as well. Okay, here's a potential problem. This one uses the state plane system. This means that before I can use this data, I need to create a copy that uses the correct spatial reference system. I'll go ahead and check the other shapefile before I do that. Okay, this one uses the state plane system as well. In the next step, I'll fix this problem with the Project tool. Using the Project tool. By now, you should be familiar with using the Project tool, but just in case, I'll walk you through it. Click the Tools button on the Analysis ribbon to open the Geoprocessing pane. Type Project in the search box and open the Project tool. For the input dataset, browse to the original folder and select the shapefile that starts with APN. For the output, name the file Parcels. For the output coordinate system, click the Select Coordinate System button. Twirl open the projected coordinate system folder. Next, twirl open the UTM folder, then NAD 1983. Choose UTM Zone 10 North from the list and click OK. Leave the other settings as they are and click Run. The parcel layer gets added to the map. Repeat these steps for the other shapefile, which represents Humboldt County. Just click the yellow file folder icon and browse to the data. Change the name of the output to Humboldt County with no spaces. You can use an underscore instead of a space. The output coordinate system should still be NAD 1983 UTM Zone 10 North, so you can just run the tool. When you are done, you should see both feature classes in the project geodatabase. Using the Extract by Mask tool. There is just one more step to complete before the data is ready to go. I want to clip the digital elevation model so that it matches the shape of Humboldt County, including the bay. I'll do this using a tool called Extract by Mask. Click the Tools button on the Analysis ribbon to open the Geoprocessing pane. In the search box, type in Extract by Mask. When you find it, open the tool. As a side note, Extract by Mask is part of the Spatial Analyst extension. If you didn't turn it on in the previous step, you'll get an error message. If this happens, go back and do that now. If no error message pops up, then you can continue. For the input raster, use the yellow file folder icon and browse to the DEM-clipped raster. For the mask data, use the drop-down menu and choose the Humboldt County layer. For the output raster, change the name to DEM. You don't have to worry about adding an extension. Leave all the other settings and click Run. When it's finished, you should see the DEM raster in the Contents pane. Mine was added to the bottom of the stack, so I'm going to move it up above the Humboldt County layer so you can see it. Originally, this raster had a big block that extended into the ocean. If you zoom in, you should be able to see that it has been clipped to match the shape of the coastline and Humboldt Bay. There is one last step you need to take before starting the analysis. Take a moment to remove the default Esri base map from the Contents pane. My default base map is called Dark Gray Base. Yours will probably be something different, like World Topographic Map. Just right-click and remove the default Esri base map. You'll also need to remove the reference layer if you have one. Mine is called Dark Gray Reference since it comes with a dark gray base map. When you're done, you should only have the DEM, the parcels, and the Humboldt County layer loaded into the Contents pane. Using the raster calculator. In this step, I'm going to show you how to use the raster calculator to model elevation at or below sea level. Before we begin, take a moment to inspect the data. You currently have a digital elevation model, or DEM, loaded into the Contents pane. A DEM stores elevation relative to mean sea level in each pixel, creating a continuous surface of elevation values. Right-click on the DEM in the Contents pane and open the Properties. Navigate to the Source tab. First, I want to check the linear unit, which you can find by twirling open the Spatial reference group. I know that this layer uses the UTM system for its spatial reference. The UTM system typically uses meters as its linear unit, but it doesn't hurt to check. So what does this mean? This linear unit tells you that the length and width of each pixel is measured in meters. You'll also need to know this in order to determine how much area each pixel represents. You can find this out by checking the cell size. Scroll up and twirl open the raster information group. Here we can see the number of columns and rows in the dataset, the number of bands, and the cell size. You learned about cell size in a previous course, but to refresh your memory, the cell size represents the footprint of the pixel on the ground. In this digital elevation model, each pixel represents just under 9 by 9 meters on the ground. This represents an area of around 80.36 square meters. Other important details to consider are the pixel type and the pixel depth. The pixel type is floating point, so we can expect elevation values that contain decimal places. The pixel depth is 32 bits, so each pixel can store a pretty large number of digits. The number of bands is 1, which is typical for a grayscale raster. You would normally only see more than one band if your image was in color. Those have 3 bands, one for blue, one for red, and one for green. Or if it also contained other parts of the spectrum, such as the near infrared you would see in a Landsat dataset, you might have 7 or more bands. In this instance, the DEM only has 1 band. Go ahead and close the layer properties. Click the Tools button on the Analysis ribbon to open the Geoprocessing pane. In the search box, type in Raster Calculator. When you find it, open the tool. The Raster Calculator is a tool that allows you to perform mathematical operations using the pixel values in a raster. You can use one or more rasters in your calculations. In this step, you will only use one raster, the digital elevation model. Our goal is to find out which areas represent the ocean. To do this, you will use the raster calculator to find areas with an elevation of less than or equal to 0 meters. Remember that An elevation of 0 is at sea level. Anything below 0 is underwater. Double-click on the DEM layer, then click on the less than or equal sign, and then type 0 to build the expression. DEM less than or equal to 0. Name the output sea level with no spaces in the name. When you're ready, run the tool. A new raster layer consisting of pixels with a value of 1 or 0 is added to the contents pane. In computer code, a 1 usually represents true, and a 0 usually represents false. The expression in the raster calculator was DEM less than or equal to 0. If the condition was true, the raster calculator assigned a 1 to that pixel. If the condition was false, the raster calculator assigned a 0 to that pixel. In this instance, all of the pixels with a value of 1 represent an elevation of less than or equal to 0. The ones here represent areas at sea level or below. Everything above sea level gets assigned a 0. Take a moment to look closely at where you see elevations at sea level. On this map, these areas are indicated in red. Are they what you expected to see? There are only a few places on the map at sea level, portions of the coastline, and areas around the bay. This tells us that, based on the DEM, the majority of the map is currently above sea level. In the next step, you'll model areas that would be inundated by sea level rise at various heights. Skill drill, raster calculator. In this step, you will create a model of sea level rise at specific heights. You will model what happens if the sea level rises by 1 meter. Then you will repeat the steps to model a sea level rise of 2 meters, 5 meters, and 10 meters. Conceptually, this is what it would look like. The baseline will be the current mean sea level. This green region represents the land currently above sea level. To model how much land would be underwater if the sea level rose by 1 meter, you would subtract the mean sea level elevation from a 1 meter elevation. What you'll get is this tiny area in between. So this region would represent a 1 meter area of inundation. You would do the same thing for a 2 meter sea level rise. Subtract the mean sea level elevation from a 2 meter elevation, and then you get a region representing a 2 meter area of inundation. The same goes for a 5 meter sea level rise. This is where things will start to get dramatic. All of this area would be underwater. The final model will be for a 10 meter sea level rise. Remember, you are subtracting the mean sea level from the areas on the digital elevation model that are up to 10 meters high. What you have left is everything that would be in between. So this is how you're going to be able to measure the total land area that would end up underwater. The way you would do this in ArcGIS Pro will be to use the raster calculator. When you created the model of mean sea level using the raster calculator, the result was a raster dataset made up of ones and zeros. The ones represented the water at mean sea level, and the zeros represented all the land above sea level. This layer will be the baseline. The next step is to create models of sea level rise at different heights, the same way you created a model of mean sea level. Instead of using an elevation of 0 in the raster calculator, you will use an elevation of 1, 2, 5, and 10 to create raster datasets representing the water rising to different heights. To figure out how much land this represents, you subtract the mean sea level raster from these new raster datasets, leaving only the land in between. The result will be a raster model representing strips of land along the coast that will be flooded by sea level rise. In ArcGIS Pro, open the raster calculator. This time you'll enter the expression dem less than or equal to 1. Name the output sea level rise 1 with no spaces in the name. When you're ready, run the tool. A new raster layer is added to the contents pane. The result is a model where the ocean has risen 1 meter in height. Here, the pixels with the value of 1 represent the water, and the pixels with the value of 0 represent the land. Next, you need to use the raster calculator to subtract the mean sea level from this data set so that you only get the land in between. So in the raster calculator, the expression will be sea level rise 1 minus sea level. Name the output inundation 1 with no spaces and run the tool. I'll zoom in a little closer so you can see the results. In this model, a 1 meter rise in sea level will impact a narrow strip of land along the coast. On the written instructions, it asks how much land appears to be between 0 and 1 meters. You may need to zoom in and toggle between the two layers to see the pixels that are between 0 and 1. In your lab report, you don't need a specific number. Questions like these are mostly used to get you to think about the results of your analysis. You can describe it by saying something like a narrow strip of land approximately 10 to 30 meters wide along the coastline. Take a moment to do a little housekeeping to keep things organized. Remove the sea level rise 1 layer from the contents pane. You won't be needing it anymore. You're going to have to do this 3 more times. One for the 2 meter sea level rise, 5 meter sea level rise, and 10 meter sea level rise. I'll walk you through it one more time before I let you do it on your own. So first, I'll create a 2 meter sea level rise raster dataset. The raster calculator doesn't automatically update from the contents pane, so you'll need to close the tool and reopen it. Okay, I'll enter the expression dem less than or equal to 2, and I'll call it sea level rise 2. Then I'll subtract the mean sea level from sea level rise 2. I'll call the output inundation 2. Then to keep things organized, I'm going to remove sea level rise 2 from the contents pane. Okay, so I've walked you through it twice. Now it's your turn to try. Repeat these steps for 5 meters and 10 meters. Remember, you'll need to close and then reopen the raster calculator each time to reset the tool. Creating a summary table. The next question we need to answer is, what types of land are impacted by sea level rise? Is it farmland, residential areas, or recreational areas? To figure this out, you must create a raster dataset representing the different land use categories. For now, uncheck all of the raster datasets in the contents pane and turn on the parcels layer. Mine is all the way to the bottom of the contents pane, so to see it properly, I'm just going to drag it to the top. Take a moment to look at the attribute data. Under the field EXLU4, you will see a number of land use categories. Because the land use categories are stored as text, we won't be able to use this type of data in the raster calculator. In the next few steps, you are going to create a field that will store the land use categories as numbers that can be used in the raster calculator. You will also group some of the land use categories together as well. That means that some of the land use categories will be assigned the same number. Right-click on the EXLU4 field and choose Summarize to open the Summary Statistics tool. Use the drop-down menu for the field and choose EXLU4. The statistic type should default to maximum, but take a moment to make sure. If it's something else, change it to maximum. And that's it. You can leave all of the other settings and click OK. In the Catalog pane, navigate to your Project Geodatabase and locate the table. Mine is called Parcel Statistics because it came from the Parcels layer. If you named your parcel layer something else, then look for a table with a similar name. Right-click on the table and open it. So what are we looking at? The Summary Statistics tool gathered up all of the unique values from the EXLU4 field in the Parcels Feature Class Attribute table. Then it counted how many parcels you have for each land use category. If you scroll down, you can see that there are a total of 37 different categories, including a blank one at the top. 79 parcels in Humboldt County don't have a land use category assigned to them. A summary statistics table is a good way to find out information about the data set as a whole. For the next step, you're going to classify the land use categories by assigning them a number from 1 through 9, creating a use code field. According to the written instructions, we are going to use 9 different use codes. We'll assign a number 1 to parcels classified as city, a 2 for parcels classified as agriculture, including timber production. So if you look at the parcel statistics table, you'll see that we have agriculture, agriculture vacant, grazing timber vacant, timber production, and timber production vacant. All of these land use categories are going to get a use code of 2. Next on the list is all categories of residential. Those are going to get a use code of 3. So if you look at the parcel statistics table, you'll need to look for any land use category with the word residential. I can see that there are about 6 categories that have the word residential. All of those will be assigned in number 3. So I hope that makes sense. Just read through the list in the written instructions and assign each category the correct number. So how do we do this? The first step is to create a new field in the parcel statistics table to hold the number. Name the field use code with no spaces in the name. The data type should be short integer since we will be using whole numbers with no decimal places. By default, all of the values are currently set to null. I find that having null values present sometimes causes problems. So one thing I like to do is initialize the field with some default values. I'm going to use the Calculate Field tool and set all the records to 0. This is just my personal preference. It confirms that this is a numeric field and helps to prevent bugs in the software from causing problems. Okay, so now we have to assign each of these land use categories a code from 1 through 9. There are several different ways to do this. One of the new features in ArcGIS Pro is that you can type directly into the attribute table. I'll demonstrate this for you. Looking at the list, I can see that the city category gets assigned a use code of 1. So I'll just type in the number 1. Just double-click to enter edit mode and replace the 0 with the number 1. Now, to make this permanent, you have to save your edits. If you look up at the table ribbon in the Manage Edits group, you'll see the Save button. Just click that to save your edits to the table. This is different from saving your project, which is the button all the way on the upper left. Easy, right? Another way to update the use codes is to select the records you want to change. Then run the Calculate Field tool. I'll demonstrate this with the next category, Agriculture. I'm going to click on the very left side of each record while holding down the Control key. I want anything that says Agriculture or Timber. Okay, now with these records selected, I'm going to run the Calculate Field tool and set the value to 2. Whenever you have records selected, the Calculate Field tool will only work on the selected records. It will leave all the other records alone. Okay, it looks good. I'm going to clear my selection before moving on. SQL Practice. Our table only has 37 records. It's tiny. But what if you had a table with hundreds or even thousands of records? Directly selecting records might not be optimal. A more robust way to work with large datasets would be to use an attribute query. I'll demonstrate how to do this for the next category, which is all the ones with the word residential in them. Click on the Select by Attributes button to open the Select by Attributes tool. Make sure that the selection type is set to New Selection. Begin the query with where EXLU4 is equal to, then use the drop-down menu and look for the next category on the list with the word residential in the name. So here it is, multifamily residential. Go ahead and add a clause. Now, this step is important. Make sure that you choose the OR operator. Whenever you want to choose multiple values in the same field, you always need to use OR. If you try to use AND, it won't work. Why is that? In SQL, the AND operator works only if both conditions are true. Each record in the EXLU4 field has only one unique category. For example, you're not going to see a single record that is both city and timber production. It's one or the other. That's why you need to use OR. You're checking for multiple conditions in a single field. Okay, let's finish this statement. OR EXLU4 is equal to multifamily residential vacant. I'll add a clause. OR EXLU4 is equal to rural residential. I'll add a clause. Or EXLU4 is equal to rural residential vacant. I'll add a clause. Or EXLU4 is equal to single family residential. I'll add a clause. Or EXLU4 is equal to single family residential vacant. Okay, that's all of them. Now I'll run the tool. With all of these selected, I'll use the Calculate Field tool and set these records to 3. It looks good. Don't forget to clear your selection. Okay, so I've shown you 3 different ways to assign use codes. I'll let you decide on how to finish the list. Just one more thing. If you come across a land use category and you're not sure where it goes because it doesn't seem to fit anything on the list, just assign it a number 9. This includes the blank record. Performing a table join. Okay, I have assigned all of my land use categories a number between 1 through 9. The next step is to get these numbers into the parcels attribute table. We can do this using a table join. Go ahead and close your parcel statistics table. In the contents pane, right-click on the parcels layer, then go to Joins and Relates, then Add Join. Okay, I got lucky because ArcPro filled out everything for me, but it's always a good idea to double check. The input table is going to be the parcels feature class. The input field is EXLU4. The join table is going to be parcel statistics, and the join field is also going to be EXLU4. Okay, everything looks good, so I'll click OK. So now when I look at the attribute table for the parcels feature class and scroll all the way to the right, I can see that the parcel statistics table was tacked on. This is a temporary condition. To make this permanent, you need to export it as a new feature class. Just right-click on the parcels layer in the contents pane and go to Data, then Export Features. I'll name the output Land Use. Actually, I don't want to confuse it with the parcel, so I'll call it Land Use Code. That will remind me that this feature class has the codes we need. After the Land Use Code feature class gets added to the contents pane, go ahead and remove the parcel layer. You don't want to mix them up later. Vector feature class to Raster Dataset. Now that we have the land use categories coded with a numeric value, you're ready to convert this vector feature class into a raster dataset. On the Analysis ribbon, click the Tools button. In the Geoprocessing pane, type in Polygon to Raster in the search box and open the tool. For the input feature, choose the Land Use Codes layer. Set the value field to Use Code. This means that the pixels in the raster dataset are going to be assigned a value from 1 through 9, depending on the land use category. This is the reason we made the parcel statistics table. This value field requires a number. In our original parcel layer, the land use categories were all text. Okay, I'll call the output land use with no spaces in the name. The next step is important, so don't skip it. We want the resolution or cell size of our raster dataset to match the rest of our data. Click the yellow file folder icon and navigate to the project geodatabase. Choose the DEM raster dataset. So now when we run the tool, the output will have the same cell size as the DEM. One last thing, make sure the box is checked next to Build Raster Attribute Table. When you're ready, go ahead and run the tool. To see the results, uncheck the Land Use Codes feature class in the Contents pane. Okay, so now we can see that we have a raster dataset in 9 different colors. Each color represents a different land use category. Take a moment to look around. What kind of land use categories are around Humboldt Bay? On my map, I see a lot of red, which is agricultural and timber. But there are other categories as well. Your map might look different depending on the color scheme. On this map, gray represents city. Light blue represents parks or open spaces. So when you think about rising sea levels, the consequences will be different depending on what types of land are flooded. That would be important information for city planners and county officials to know. In the next step, we're going to figure out how much land in each category is impacted by different heights of sea level rise. Impacts on land use. Currently, our inundation rasters are made up of pixel values that are either 1s or 0s. The land use raster is made up of pixel values from 1 to 9. These numbers represent different land use types. By multiplying the two raster datasets together, we can find the impact of sea level rise on different land use categories. Any pixel from the land use raster multiplied by a 0 on the inundation raster becomes a 0. Any pixel from the land use raster multiplied by a 1 on the inundation raster remains the same. The result is a raster layer with numbers 1 through 9, representing the land use categories impacted by sea level rise. My contents pane is getting a little crowded, so I'm going to do some housekeeping before I continue. I'll remove the Land Use Codes feature class, Humboldt County, and the parcel statistics table. I don't need those layers anymore. Next, I'll open the raster calculator. I'll start by multiplying the land use raster by the 1 meter inundation raster. I'll call the output flood 1m. Close the raster calculator when you're done. Okay, let's look at the results. Make sure to uncheck the land use raster, which doesn't have the cutout for Humboldt Bay. These are the land use categories that would be affected by a 1 meter sea level rise. It's only a small strip of land along the coast. Remember, this is a very simplistic model. This is strictly based on an elevation model, which may or may not be very accurate. It also doesn't factor in tidal variation or storm surges. However, for our purposes, it does give us a general idea. I'll go ahead and walk you through the next one before I let you work on your own. Okay, so I'll reopen the raster calculator. I closed it earlier to refresh it. Then I'll multiply the land use raster with a 2 meter inundation layer. I'll call the output flood 2m. Okay, let's look at the results. There's a lot more happening with a 2 meter sea level rise. Just to be safe, I'll uncheck the 1 meter flood layer. I noticed that the colors changed from the original land use raster. This is because we have an extra number, 0, which is the gray areas on the map. Remember, a 0 means that the land is above the water. Everything else is underwater at this point. So all this orange area that's flooded is agricultural lands. The red regions are city parcels. The medium blue are parks and open spaces. So by combining the land use with different flood levels, we're already getting a lot of information. I'm going to let you do the next two. Use the raster calculator to multiply the land use raster by the 5 meter inundation layer, then the 10 meter. If you're following along, pause the video and come back when you're ready. Calculating areas on a raster dataset. Up to this point, you probably have had some experience calculating areas using vector datasets, such as shapefiles or geodatabase feature classes. In this step, you'll calculate the areas impacted by sea level rise using a raster dataset. If you will recall, when you created the land use raster, you selected an option to build a raster attribute table. To see what that looks like, right-click on your 1 meter flood raster and open the attribute table. You should see 3 fields, an object ID, a value, and a count field. We'll only be using the second 2 fields to calculate the area, the value field and the count field. The value field contains the land use categories from 1 through 9. The 0 represents everything above the waterline, which is outside of our area of interest. The count field represents the number of pixels in each category. We'll use this information to calculate the area. Once you know the area of a single pixel, you can determine the area based on the number of pixels. For example, suppose you had a raster dataset where the cell size was 10 meters. That would mean that the width of each pixel represents 10 meters on the ground. Likewise, the height of the pixel was also 10 meters. To get the area, you multiply the width by the height. In this case, 10 meters times 10 meters gives you 100 square meters. Okay, so given that a pixel represents 100 square meters, what would be the area of, let's say, 5 pixels? To get that, you'd multiply the number of pixels, in this case 5, by the pixel's area. In this example, that would be 100 square meters. So 100 times 5 gives you 500 square meters. You can apply the same process for the flood rasters. They have a cell size of about 8.964 meters. So 8.964 times 8.964 gives you approximately 80.35 square meters. To get the area in square meters, you would multiply the number of pixels by 80.35. However, according to the written instructions, we want the area in hectares. A hectare is a unit of measurement that represents 10,000 square meters. To convert meters to hectares, you have to divide by 10,000, or you can just move the decimal place to the left 4 times. So 80.35 square meters is equal to 0.008035 hectares. That means to get the area in hectares, you would multiply the number of pixels by 0.008035. Let's try it out. In ArcGIS Pro, add a field to the attribute table and call it area. Set the data type to double. Remember, the double data type can store decimal places. Next, run the Calculate Field tool on the area. Double-click the Count field and multiply it by 0.008035. Then run the tool. We now have the area in hectares for each land use category impacted by a 1 meter rise in sea level. Repeat these steps for each of the flood rasters. Make sure that you set the data type of the area field to double. Then use the Calculate Field tool and multiply the count by 0.008035. When you're done calculating the areas, record your results in an Excel table. Include the land use code and the land use category, and record the areas from each of the flood rasters. Save your Excel workbook to your final folder, and be prepared to include this table in a lab report. Using the Reclassify tool. For the next step, you're going to create a flood risk map using the Reclassify tool. The goal is to show the flood zones for each scenario of sea level rise on one map. Before we start, let's clean up the contents pane. For this step, all you need is the digital elevation model. Go ahead and remove all of the other layers. On the Analysis ribbon, click the Tools button and type in Reclassify in the Geoprocessing pane search box. There are multiple versions of this tool. Use the one under Spatial Analyst. For the input raster, choose the DEM from the drop-down menu. Next, click the Classify button. Change the number of classes to 6. In the upper value column, enter 0, 1, 2, 5, and 10. Leave the last value alone. This is the upper limit of the data. Click OK to accept the break values. Okay, so to help you understand what we did by setting the break values, I need to review some concepts with you. We performed what is called quantitative data classification. Remember, classification is the method of grouping something based on shared qualities, magnitude, or quantity. Through classification, you simplify a phenomenon to make it easier to understand. In this instance, we're going to simplify the elevation data by grouping it into different class intervals. There are 2 types of data classification, quantitative and qualitative. Qualitative data includes information that has a descriptive nature. For example, if we were classifying different tree species, that would be qualitative data because it can't be measured. It's a non-numerical category. Quantitative data includes information about quantities and numbers. If you're working with numeric data sets, then you're working with quantitative data. The elevation values in the digital elevation model are numeric, so we are performing a quantitative data classification. We broke the data into 6 groups. We call them class intervals. Class intervals are a range of values that do not overlap. We did this by entering the class breaks. The break value defines the boundaries between each class interval. So if you look at this table in the Reclassify tool, You can see the class intervals under start and end. The end values are the class breaks. Now remember when I said that class intervals are ranges of values that do not overlap? Based on this table, it looks like some of the start and end values use the same number. For example, the first row ends with 0, and the second row starts with 0. So which class interval actually includes the number 0? When the numbers between two rows overlap, the lower range is considered inclusive, meaning that the first row gets the 0. The second row starts with anything above 0. The same goes for the second and third row. The second row ends with the number 1. That means that 1 is included in this class interval. The third row starts with any value greater than 1. Okay, so now that you have determined the class breaks, you need to set the new values. You do this under the new column. I want this data set to show a 1 meter sea level rise, a 2 meter sea level rise, a 5 meter sea level rise, and a 10 meter sea level rise. I don't need to include the existing sea level or lower. I also don't need to include anything greater than 10 meters. I can get rid of these values in my output by setting the new values to no data. I'm going to do this now by entering no data into the first row and the sixth row. Make sure you use all caps when you type it in. You can also copy and paste it if that's easier. Now I want to set the remaining rows to 1, 2, 5, and 10 to represent sea level rise. Make sure your table looks like mine before moving on to the next step. Call the output flood risk with no spaces in the name. Check the box next to change missing values to no data, then run the tool. In the next step, I'll show you how to create a hillshade to serve as a base map. Creating a hillshade. For most maps, you don't need a hillshade. However, in this instance, a hillshade base map can provide additional context to the map reader by supplying visual clues about the terrain. On the Analysis ribbon, click the Tools button and type in Hillshade in the Geoprocessing pane search box. Again, you'll see two versions. Use the one under Spatial Analyst. The input raster for a hillshade will always be a digital elevation model. Use the drop-down menu and choose the DEM as the input. You can accept the defaults for the remaining settings and run the tool. What you will get is a layer that provides a three-dimensional effect that gives the map reader a visual sense of the terrain. I'm going to drag my hillshade to the bottom of the Contents pane. Then I will place the digital elevation model on top. I'll make the digital elevation model 70% transparent to soften the hillshade up a little. You can literally spend hours making a hillshade look nice. This step is a very quick way to improve the look of your hillshade if you don't have that much time. To give the hillshade a more natural color, you can change the color ramp for the digital elevation model. Select the DEM in the Contents pane, and then in the Raster Layer ribbon, choose the Stretch option under the Symbology button. Next to Color Scheme, use the drop-down menu to choose one of the elevation color ramps. You can check the box next to Show Names to make them easier to find. There are several choices available. I'm going to go with Elevation number 2. You can pick any one you like. Okay, so what this does is provide some color to the transparent digital elevation model. A common mistake I see is that sometimes students will add color to the hillshade directly instead of the DEM. If you do this, the map will look weird. Make sure you're adding color to the DEM and not the hillshade, otherwise it won't look right. Okay, next I'm going to change the colors of the flood risk layer. The default color scheme has a different color for every elevation category. This color scheme actually breaks cartographic convention because changes in hue are mostly used for qualitative data. Qualitative data has a descriptive nature and cannot be measured. What we have here is quantitative data, a numeric range from low to high. For this type of data, you should use a single hue with changes in value and saturation in your color scheme. Let me show you what I mean. I'll turn on the flood risk layer. If you're following along, make sure it's selected in the contents pane. This time I'm going to choose unique values. When the symbology pane opens, you should see the color scheme for each of the 4 categories. Since our map is showing elevation values for a water feature, an appropriate choice would be one of the bathymetry color schemes. I'm going to go with bathymetry number 3. So this is what I was talking about when I mentioned using a single hue with changes in value and saturation. Each of the colors is a variation of the color blue. In the bathymetry color scheme, the darker blues represent deeper water. Okay, so now we have a map showing flood risk for different sea level rise scenarios. Creating a map layout. The last step in the written instructions is to create a small-sized map to use in your lab report. It's always important to make sure that the map layout is the exact size and shape you plan to use. For example, many people will use one of the default sizes, such as 8.5 by 11 inches. Unless you plan to use the map at this size, it's a really bad habit to accept these layout defaults when designing your map. This map should be approximately 6 by 6 inches. On the Insert ribbon, click the New Layout button. Move your cursor to the bottom to scroll down until you see the Custom Page Size option. Change the dimensions so that the height and width are 6 inches. What you see here is the page size. In the next step, you'll need to add a map frame to the page. Click the Map Frame button in the Map Frames group. Select the map with the flood risk layer. Next, drag a rectangle to represent where to place the map frame on the page. It doesn't have to be perfect. We'll adjust the size and position of the map frame in the next step. Click the Map Frame ribbon. On the right, adjust the size and position of the map frame on the page. You'll need to set the X and Y values to 0. You can also adjust the width and the height of the map frame so that it matches the page size, 6 by 6 inches. To adjust the map scale and the contents of the map frame, go to the Layout ribbon. Click the button that says Activate. When you activate a map frame, it allows you to pan and zoom within the map. In this instance, the area of interest is Humboldt Bay and the surrounding regions. Zoom in so that Humboldt Bay is clearly visible. I think all of this flooded farmland below the bay is interesting as well, so I'll include that in my map extent. Once you are satisfied with the scale and extent of the map features, lock the position by deactivating the map frame. You can do this on the Layout ribbon by clicking on Close Activation. The first thing I'm going to do is add a background color to the map. You can do this by right-clicking on the word Map in the Contents pane and opening the Properties. Make sure you don't accidentally choose Map Frame. It's easy to confuse the two. On the General tab, use the drop-down menu to choose a background color. I typically choose blue to represent water features. However, the bathymetry color scheme I chose already uses blue, and I don't want to confuse the map reader. Instead, I'm going to pick a neutral gray for the background. I'll go with gray 50%. I'll add a scale bar. When you add a scale bar, make sure to adjust the size so that the units make sense and are easy to use. I'm just going to drag this one out so that it is exactly 4 miles. That fits nicely within the open space at the bottom of the map. I'll also add a north arrow. One problem I see all the time is that students will add a huge north arrow. Don't do this. You want to make sure your north arrow is small and inconspicuous. I'll also add a legend above the scale bar and the north arrow. There are a few legend styles available. I'm going to go with legend style number 2 since it comes with a light background color, which will make the legend items easier to read. By default, the legend includes all of the layers in the contents pane. I'm only interested in the flood risk layer, so I'm going to uncheck the other legend items in the contents pane under the legend group. The legend will also need some additional adjustments. I don't need to see the layer name or the field name, which are included by default. You can turn these off in the legend properties. Just right-click on the legend and open the element pane for the legend. By default, the legend elements pane tends to open in the placement group, which is the last button. Click the legend options, which is the first button. Then click the button that says Show Properties. Uncheck the box next to Layer Name and Headings. Then click the Back button to get back to the legend options. Never use the word legend as a legend title. The map reader already knows it's a legend, so using this word as a legend title is redundant. Either provide a descriptive legend title or leave it out. In this instance, a descriptive legend title would help the map reader understand the data. I'll change the title to Sea Level Rise in Meters. Then, make sure the box next to the word Show is checked. There are a ton of options you can go through to change the look and feel of the legend. For this exercise, I'm going to accept the remaining defaults. You can also take a moment to resize your legend if needed. You want it to be legible without it being too huge. Once you're satisfied with your map layout, export it as a PNG. Just right-click on the locator layout in the catalog pane and choose Export to File. Make sure the file type is set to PNG. Also, make sure the resolution is set to 300 dpi. Save the file to your final folder. I'm going to call the file Sea Level Rise. When you're ready, click Export. And that's it for this tutorial. If you enjoyed this demonstration of the tutorial Sea Level Rise around Humboldt Bay, like and subscribe. Thanks for watching.